Okay, today we're going to be talking about negative exponents, and they come directly from what we learned about with dividing with exponents. So if you felt pretty good about that lesson, this one follows nicely behind it. So the first thing you want to do is just remember that most fundamental thing we started with, that if you have fractions where the numerator and the denominator are the same, then those can all simplify down to 1. And that's the foundation for our dividing with exponents, and it also leads us into our negative exponents. The other thing you want to remember about dividing with exponents is if we have something like 8 to the 5th over 8 to the 2nd, we could write it out the long way, 8 to the 5th becoming 8 times 8 times 8 times 8 times 8. And in the denominator, we have 8 being multiplied by itself twice. Each of those that pair up, numerator and denominator, simplify down to 1. And you want to remember this equals 1. Don't just cancel them out and think they're gone. They actually represent some ones. And that becomes important as we move into our next lesson, where we're talking about 0 as an exponent. But for now, let's just stick with the negatives. So we have left in our numerator 8 to the 3rd power. So we talked about how there is a shortcut. If you look at our original question and our result, we could just find the difference of our exponents. We have 5 eighths in the numerator, 2 eighths in the denominator. These 2 eighths canceled out 2 of these eighths, so we subtract, and we're left with 3 eighths being multiplied together in the numerator. Well, with negative exponents, what ends up happening is we have more in the denominator than we have in the numerator. So let's look at what we did the other day first, and then move into those negative exponents. So for example, we have r to the 3rd, t to the 4th, over r to the 7th, t to just t. And that's t to the 1st, but we're kind of lazy. We don't like to write extra stuff if we don't have to. So you just have to remember if there's a variable there or a number there and there's no exponent, the missing exponent is a 1 that we're just too lazy to write. Okay, so let's go back to writing it out the long way. And this becomes r being multiplied by itself 3 times, t is multiplied by itself 4 times. In the denominator, we have a lot of r's. We have 7 of them. And a t. So these 3 r's right here pair up with 3 of these r's to create all of these 1s. R over r is 1. So again, if you cancel them out, just remember they are 1s that are being left behind. And then we have 1 t in the denominator that matches up with 1 of the t's in the numerator to create another 1. We don't need these 1s because we have stuff left in the numerator and stuff left in the denominator. But just in case everything cancels out, that kind of helps you remember that it's a 1 that's left behind and not a 0. But what we have left in the numerator now is t to the 3rd. And in the denominator, we have r to the 4th. And if we go back to that, find the difference between the exponents, like we did with this one, you can see that what we did here with our r's, the difference between the 3 r's that we have in the numerator and the 7 r's we have in the denominator, leaves us with 4 r's in the denominator. And our t's, remember there's a 1 here. We have 4 t's in the numerator, 1 t in the denominator. So this one cancels out one of these, leaving us with 3 in the numerator. That's what we talked about the other day. But if you look at the exponents and you think about that shortcut where we're subtracting, and if you were to subtract top minus the bottom, what we'd end up here is 3 minus 7. And 3 minus 7 is not 4. 3 minus 7 is negative 4. So the other answer that we could get if we use our shortcut is r to the negative 4, and right here, t to the third power. So what this negative 4 is doing is it's telling you that there were more in the denominator, and that this base, r, actually belongs in the denominator. There were 4 more in the denominator. That negative 4 represents that it really belongs down here because there were more in the denominator. So these are equivalent. T to the third over r to the fourth is equivalent to r to the negative 4 t to the third. These represent the same idea. They represent this, they represent this. It's just simplified down to either this or this, depending on whether you're supposed to use only positive exponents or if you're supposed to use negative exponents. So I'll give you a moment to think about that, and then we'll move on to example 2. Okay, so moving on to example 2. Now in our numerator, we have m to the 5th, n to the 2nd, and in the denominator, we have m to the 3rd, n to the 6th. And you want to focus on the variables separately. So we'll look at the m's first. If we were to write it out the long way, we'd have m being multiplied by itself 5 times in our numerator, and n multiplied by itself twice. In the denominator, we have m to the 3rd and n to the 6th. So you do not have to write it out this long way, but it's nice to really see what it means so that you can remember how to use the shortcut. If you start to get confused on a test, you can go back and say, all right, well, if I just write it out the long way, I can go, oh yeah, it is subtraction that I need to use when I'm simplifying with division. So m over m, all of these simplify down to a bunch of 1s. And there's no other m's in the denominator to pair up with those 2. So we have 2 left over. And if we look at our shortcut, we can already see that there would be 2 left over in our numerator. The n's, we have 2 n's in the numerator that will match up with 2 of the n's in the denominator, leaving us with some more 1's because n over n equals 1. And what we have left is n to the 4th in the denominator. But if you go back and look at the shortcut, if you subtract the top minus the bottom, we would still have a positive m to the 2nd power, but our n's would become n to the negative 4. And that's just if you are showing that there are more n's in the denominator, really, because when you subtract 2 minus 6, we get a negative 4. There are more in the denominator, but technically you're writing it in the numerator here. And to show that it doesn't belong in the numerator, that there were actually more in the denominator, you use that negative exponent. Or you can just put it in the denominator. So again, these are equivalent. And the negative exponent is just showing you that this really belongs down here. And once we put it where it belongs, it becomes a positive. So more on that with example 3. Okay, so if you wanted to write that down to help you remember, the negative exponent tells you that the base isn't where it belongs. And that same fundamental piece of information still holds true. The exponent only affects what it's next to. So if one base has a negative exponent, it's only affecting that base, and the other variable or number or base of whatever form that is there, if it's not being affected by the negative exponent, it's right where it belongs. So let's go ahead and show an example of that to make it a little bit more concrete. So let's say I have c to the negative 3 being multiplied with d to the 2nd power. And we want to rewrite this so that we don't have a negative exponent there. What is happening here is that this -3 is affecting the C, the 2 is affecting the D. This is a positive exponent, so our D is right where it belongs. It is sitting, if we wanted to turn this into a fraction, it would be over 1, and it is sitting right where it belongs in the numerator. But this C to the -3 is saying that the C to the third power really belongs in the denominator. There were more C's in the denominator. So this could have come from another problem, like let's say it started out as C to the second, D to the second, over C to the fifth. You can see how you could subtract these and end up with C to the -3rd. You can also tell that there are more C's in the denominator, 3 more in the denominator. So maybe this is where this expression came from. This one also could have come from this. But it just kind of reminds you there were more C's in the denominator. And that's how that happens when you're subtracting. Another thing that you might be asked to do is you might be given a fraction with positive exponents. And they're saying, rewrite this expression so that it is no longer in fraction form. Well, if you wanted to write this so that it's not in fraction form, you have to move this out of the denominator. We want to create something where it's over 1, because we don't write that fraction. You wouldn't say you're 14 over 1 years old. So we're going to move this so that it's in the numerator, and then we don't really have it written as a fraction anymore. So our u to the third is right where it belongs. It stays u to the +3. But this v is in the denominator, and we need to represent that it's in the denominator by moving it from the denominator to the numerator and making that exponent negative to remind us that it really belongs in the denominator. And if you were going to write this without a fraction at all, of course, it would be u to the third v to the -5th. That over 1 is just the extra stuff that we don't write. Thank goodness, because who wants to write all that? So if you want to watch this over and over again until it makes a little bit more sense, it's kind of nice that you can do that. You can pause it, you can think about it. And we'll be talking about this at our Zoom meeting this week. If you're watching it after the Zoom meeting, you can still contact me if you have any questions. But hopefully this helps explain negative exponents. See you later.